Hi, good evening. I hope I'm audible and the slides are seen. Looks like it's just you for now. Let's see if more people join. But yeah, I'll anyway start the class or we'll get late. So yeah, so this is about week 7's summary for the course Essentials of Data Science with R Software, Probability and Statistical Inference. So yeah, here we have the professor has discussed about distributions involving continuous random variables. So we'll discuss normal distribution, continuous uniform distribution, and exponential distribution in this lecture. And yeah, so before I start the lecture, I just recall that in the last week's live session, somebody had asked a question. When you run, like for example, for Poisson distribution, if you run R poise, and if you run like R norm or R binorm. So when you run the R command to generate random variables, does it give only integers or does it give decimal numbers? So yeah, I'll answer the question now. So it depends on what kind of a distribution you're working with. So if it's a distribution that involves discrete random variables. So these were the distributions that we discussed in the previous class, like binomial distribution, geometric distribution, and the distributions that we saw in the previous week. So those dealt with discrete random variables, which are just whole numbers, like number of people in a room. So number of people cannot be 2.5. It can be either 2 people or 3 people. So such random variables are called discrete random variables. And the distributions dealing with them, when you like generate random numbers with such distribution, it's a whole integer. And in this week's lecture, we are looking at distributions involving continuous random variables. So when you simulate the random variable function to generate random variables for given distribution, it gives you decimal numbers because these distributions uh, talk about continuous random variables. So yeah, that answers the question somebody had raised in the previous lecture. So yeah, with that said, let's start this week's summary. Slides are not moving. So yeah, the first lecture 38 was about continuous random variables. So like we said, continuous random variables could take decimal numbers as well. So it could be like height of like height of people in a class. So this can be like 157.5 centimeter, 172.3 centimeter, and so on. So it could take decimal values. Or it could be like any such measurement or temperature in a particular day. So this could be 32.5 degrees Celsius. Sorry, Fahrenheit. Yeah, 32 degrees Celsius. Or it could be 30, or it could just be like 18.2 degree Celsius and so on. So all these take decimal numbers. So the distributions that model such continuous random variables or so yeah, we talk about one of such distribution. It's called a uniform distribution. That is the first distribution that we're going to look at. So before that, like we know that random variable, it takes up a probability density function, integral like lower limit, upper limit, like minus infinity to x or minus infinity plus infinity, f of x dx. And also like, so it measures the given area before a specific point. And also, there's one more thing that continuous random variables, the probabilities are zero if you look at a specific point. So if you look at the probability at x is equal to 2, the probability would be 0 because, yeah, you're just looking at the point. So you always look at an interval here. So the probability of x falling between 0 to 2 would be a given number. This would take some value. So that's what this line means. And yeah, so let's look at continuous uniform distribution now. So here we have 2 points, A and B. So it's always written as, so X is the continuous random variable and it follows a uniform distribution. And these are the two parameters, 2 points, A and B. So generally B is greater than A. So it could be like any number. So these A and B could be any numbers. And yeah, like you could see in this graph, this is x-axis, these are your given points, the random variable x, and y is your f of x. And yeah, so f of x is given by 1 by b minus a. So you're looking at these 2 points. So for any value of x between a and b, you will have this given probability density function for this. So any value below a or above b, you'll have 0. Your f of x would be 0. That's what this means. So if you look at this, this is like a rectangle. So generally, basically, CDF is when you calculate the area of this rectangle, right? I mean, this probability density function, you're calculating the area of the rectangle. So we know that area is equal to length into breadth. So the length here is b minus a, like this point minus point, that gives you the length into breadth. So this would be the breadth. Let's say this is a given probability value. So if you calculate this height, this one, you'll get the probability. So this basically is your probability value. So yeah, breadth is your probability. And area, so always the probability, the area would be 1. So now when you rearrange this, you have 1 by b minus a. So that's what is given here. So yeah, between a given two given values, your probability is 1 by, like your PDF is 1 by b minus a, and otherwise it's 0. That's what it is here. And then the mean and variance of such a distribution, mean E of x, expectation of x, would be a plus b by 2. So this is intuitive because you just take the average between 2 points. So a plus b divided by number of points are 2. So a plus b by 2. So this is the mean here. And the variance, this can be calculated by b minus a the whole square divided by 12.
Excuse me, madam. Excuse me, madam.
Uh,
Madam, madam, I have a question.
yes.
Previously, I asked, madam, like, what will be the question paper pattern? I asked you. Can you please
Okay.
give us some pointers on that one, like question paper pattern in the main exam?
So it will usually be like your assignments, but yeah, but you will not be
Good.
asked questions that where you have to work with R because you won't have access to R like when you give
Okay.
your exams.
Okay.
So yeah, it should just be like straightforward questions where you can easily solve them, or
Okay.
some questions like that, like MCQ, multiple choice questions, mostly.
Okay. Okay.
Oh yeah. I could just confirm
And
this and answer this better in the next class as well. But yeah,
okay,
this is
madam.
how the pattern usually is.
Yes, yes, madam. Please,
And
please, madam.
especially in this class, we'll look at, so we'll deal with a distribution called normal distribution. So for that, you either need a table, a log table, like a normal distribution table to find out your answer, or you need an online tool, which we'll discuss. So in your exams, you won't have access to that.
Okay.
So yeah, and you won't be given such questions, but all these assignment questions are just for your practice, and so you could understand and use it later on.
And one more thing, madam, like how to excel in this, madam, like how to problems, how to gain the problem solving capability and all. Like
Yeah,
what
I
is the
just
way you followed? So
okay.
that is my question. Like how did you invest your time and how did you come up with the
Mm,
expertising?
mm.
That
Yeah,
is
I
my
just saw your email. So
question.
yeah, to answer that, I did not like follow any such course, to be honest. Like, yeah, so basically your mathematics concepts have to be strong. So all these that we're looking at are the basic probability concepts. So you should
Yes.
have, it's not that you should remember every detail of it, but when you go
Okay.
back and read, you should immediately like be able to recall, like you should be able to understand it. So that's the most important thing.
So
And
which what steps did you follow? Like
yeah, what steps I followed was, so I work, so right now I'm doing my PhD, and before that I worked as a research assistant. So I did bioinformatics. So I just
okay.
use such computational tools to analyze biological data, like
Okay.
DNA sequences and such data. So
Okay.
that's when I learned bioinformatics when I started working. So that for that I needed a lot of R. So I did not have any previous experience with R, or I did not have any such exposure. But how I learned was, so generally such data you'll be having text files. So the basic
Okay.
thing that I started with was text file handling. Like how do you read a file? How do you read each column of a file? And like let's say you have like number like people, different patients, and you have the blood group of the patient. Like I just want to filter out the patients with O blood group. Like how will I filter that column? Such
Okay.
text formatting and filtering. So like these are some basic things that I started with. So whenever I wanted to know, I would just like, so there are resources like Stack Overflow,
Okay.
what is the other one? I don't remember that. Stack Overflow, and there's one more resource where, yeah, you would find such solutions of how to deal with such problems with R, or some people must have answered such questions. So at that time,
Okay.
yeah, it's just like a Google search and using these resources. But now, yeah. So that's how I just started learning. So I think that's how most of the people would start.
So I'm asking
the
about
same.
the problem solving ability. Like this one, you worked on more examples or like that? Because more worked examples did you follow from any book?
Like these, like you mean the ones that we solve in
Yeah,
the
yeah, yeah.
uh
Should we
this
work more on worked examples or something like that from
uh
various books?
not I generally don't refer to books. So we just have the answers. So based on the lectures that I teach, I just try to apply the formula and see if I'm getting the correct answer. So that's
Okay.
what I generally do. If I don't get the answer, I try to like refer something. But yeah, usually it's not been a problem. So,
Okay.
yeah.
Okay, madam. You can continue, madam.
Okay. Yeah. We could discuss this later as well.
Okay. Okay.
So yeah, here again coming back to the lecture, we were talking about this how to calculate the mean, like A is B divided by 2, and variance could be calculated with this formula. This is something you should remember. So B minus A the whole square by 12. So this is continuous uniform distribution. And there's one more thing that was just mentioned, something called uh, inverse distribution, like inverse transformation method. So like for example, you take, you have a number and you take a square root of a number, you get a specific value. And again, if you take a square of this value, you go get back to this original value. So this is something like inverse. Like, so here, for example, let's say, yeah, so X random variable follows a function F inverse of U. So which means like the, sorry, uh, so U must be 1 by X here. So yeah, X follows inverse function of 1 by U. So let's look at a better example. Although, suppose we want to generate a random variable X having the distribution function, the probability distribution of a random variable is given by X power N. So now how will you calculate X now? Yeah, from this. So X should be, so yeah, this you denote by U. U is equal to X power N. Now how will you go back to calculating X? So in this case, X would be U to the power 1 by N. So this is just like some inverse function. You take the inverse of it. And similarly, you have a uniform distribution function, which is 1 minus e power minus X. So it can also be written as e power minus X is equal to 1, you take U this side, 1 minus U. And now how do you calculate X? If you take a logarithm from both sides, you get minus X is equal to log of 1 minus U. And yeah, you just multiply by minus on both sides. You get X is equal to minus log 1 minus U. So yeah, when you have either one, like if you have U, you can calculate X, or if you have X, you can calculate U. So by using such inverse transformation method. So this is what these two slides talk about, although we have not used this anywhere in the problems that we would solve. But yeah, it's just for you to know. So here's a simple example of continuous uniform distribution. So we have seen this example several times. Like you are waiting at a train station and this train or bus, it arrives every 20 minutes. So what is your wait time? And the function PDF is given by 1 by 20. Now, how will you calculate? So you need to calculate the probability of waiting time between 5 to 7 minutes. So P of X between 5 and 7 is given by integral of 5 to 7 f of x dx. Here f of x is 1 by 20. So 1 by 20, you apply upper limit minus lower limit. So if you just do this, it's basically 7 minus 5 by 20. You get this answer. Similarly, you can calculate 18 minus 2 by 20 for between 2 and 18 minutes. So yeah, that you can also like graphically represent it this way. So you have 0 to 20 and you want to calculate between 5 and 7, 1 by 20, your distribution would look like this. And between 2 to 18, your distribution would look like this. And also, like we saw, the mean, the average waiting time would be A plus B by 2. So it can be calculated by, so your A is 20, 0, B is 20, divided by 2 is 10. So 10 minutes is your average waiting time. Yeah. And from this, you can calculate variance as well. B minus A square by 12. So if you calculate this, you'll get your variance of X. So yeah, now let's look at normal distribution, which is the very widely used distribution that you'll come across in data science. And yeah, if you have some data that and you see a normal distribution data, it's generally, yeah, it feels nice because yeah. So a random variable X is said to follow a normal distribution with parameters mean, mu, and variance sigma square. And its PDF is given by this huge formula. You don't really have to remember it because, yeah, we won't be applying this formula to solve any problems. But yeah, it would be good if you can remember it, but you really don't have to remember it. So yeah, let's look at this distribution. So this is denoted by, so X is a random variable following a normal distribution where we have two parameters, mu and variance, sigma square. And so variance is sigma square. So standard deviation is the square root of variance. So square root of sigma square is just sigma. So standard deviation is sigma. So these are just some things that you should know. So yeah, here mean variance. And so this distribution, let us look at a picture. Yeah. So anything that looks like this, so any curve that looks like this is a normal distribution. Like it could be like this as well. It just has to be symmetric around the mean. So this is the mean. Wherever you have the peak, that is your mean. And yeah, so this is your variance. So the total area of, yeah, we'll look further about this curve. So yeah, the value of E of X mu determines the center of the probability density function, and the value of variance determines the width. So there's one more thing called standard normal distribution. Somebody saying something? Okay, then yeah. So we saw that the curve looks like this. This mean could be any value. It could be 10, it could be 2, it could be 5, or the mean could be any value. But a standard normal distribution when your curve is symmetric around 0. Like you normalize all your whole data set such that your mean is 0 and variance is 1. So mu 0 and variance 1. So that is when you call it a standard normal distribution. And it is denoted by this. So X such that X is a random variable following a normal distribution. mu 0 and sigma 1, sigma square 1. So yeah, we use the standard normal distribution just to make the calculations easier. And yeah, it's given by a PDF, which is you denoted by this formula, which again, you don't need to remember at this point. Yeah, we just saw this. And yeah, so the mean denotes the peak and the flatness, the variance denotes the flatness of the curve. So if your variance is small, then your curve will be narrow. So your bell will look narrow if your mu is small, if your variance is small. If your variance is large, it'll be widespread. Variance is basically your deviance, like your deviation from the mean. So if the deviation from the mean is high, the spread will also be higher. So that's what this means. And also for this normal distribution, so if you have the value of mu, you cannot derive the value of sigma square. And if you have the value of variance, you cannot derive the value of mean. Because yeah, these are just independent measures for this distribution. So here is an example. It shows you a curve that has same mean, which is 5, but it has different variances. Variance of 1 will look like this, and a variance of 4 will look like this. So just with the value of mean, you cannot say how the distribution looks like. You need both mu and sigma square values to exactly say how the curve looks like. And yeah, so these two, the two, okay, never mind. Yeah, so this curve, right. So this curve and this curve, these two have the same variance as you can see, but they have different means. So they are shifted along the x-axis. So yeah, this is just to show you that you cannot just have one value and say something about the other value. So that's all. And you can also denote the CDF of a normal distribution as 5. So we denote PDF of a random variable x as f of x, right? Like here we saw f of x. But in case of normal distribution, your CDF can be defined as phi of x. So this is phi. CDF is denoted by this, and we'll look at that. And also, for any constants.
Can you explain that diagram once again?
This one?
Yeah. What is that?
So it is just telling you that you have mu. Let's just say you have a problem statement where your mean is 10. But you cannot do anything with only this value because you cannot derive the variance from this value. That's what this curve is saying. So let's say this is your x-axis, 5, 10, 15, 20. These are your random variables here. Sorry. And this is your probability f of x. So if you have a mean of 10, your curve is basically symmetric here, around 10. But if your variance is small, like if your variance sigma square is 1, your curve will look like this. But if your variance is larger, like if it is 6, your curve will look like this, but it will still be symmetric around 10, but it will be flatter if your variance is large. And also, if you let's say you have the same variance, you have variance is equal to 1. You cannot say what the mean would be. Just with this variance, you cannot derive from this saying, oh, mean could be 1. This is not the case. Your mean could either be 10, it could be like this, or your mean could also be 20. So in this case, your curve will be symmetric around 20. So this is just, yeah.
Depends upon the second order movement of the random variable, it is varying that variance. Expression of x square. For same mean, we will get different
No,
variance
like
you are
these are just independent measures. With one value, you cannot say that the other value can be this. You cannot guess what the variance can be. So you for calculating a normal distribution, you have your given data has to be mean and variance.
same means versus same variance. Different how it is, ma'am? Same means versus same variance. What is the
Oh, this is,
uh,
I mean, this figure is just showing you like how your curve looks like. So you have same mean. So these two curves, curve number 1 and curve number 2, they have same mean, but they have different variances. So your curve looks like this. But for different means and same variances, your curve looks like this. So that you just, this is what this line tells you. For same means, your curve looks like this. And for same variances, your curves look like this. The flatness of the curve. If your variance is same, yeah, the width of the curve will be the same. But the height of the curve will be different. Is that clear?
oh, okay, but same variance, say for same mean we will get different variances. Okay,
Yes.
but that is accepted. But the same means same variance means
Yeah, if you have same mean and same variance, your curve will look exactly the same for two distributions. Like, let's say I get one data from one person, one data from the other person. If they both have same mean and same variance, your curve will look exactly the same.
if variance is large, if variance is small, what we will say about that data?
Yeah, that's what I'm saying. If variance is small, so what is variance? So variance basically means how spread the data is from the mean. Let's say mean, most of the points lie within this range, but some points lie here. So, but still the variance for this would be small. But if you look at points that looks like this, which are widespread, here the variance is larger. So variance is basically how much your data points are spread from a mean value. Is that clear? Yeah.
Oh,
Is
yes,
that,
ma'am, yes, ma'am.
yeah.
I can understand.
Yeah. So if like same way in this curve, let's say this is your mean. If your variance is small, what will happen? There won't be much spread. So all your data points will be concentrated around this mean. If your variance is small. Variance small. But if your variance is large, the data points will be widespread. They'll be far away from your mean. They'll look like something like this. Yeah, they'll just look flatter. Small variance will look like this. Large variance will look flatter. So the curve keeps getting flat as the variance increases.
Okay, ma'am.
Yeah.
Ma'am, what can we say about the data? Suppose variance is very small means the data. Anything can we say about the data?
Yeah.
Suppose we are having any data, the variance is very small. Suppose very large. What we will say about the data? Any examples for the any example data?
Mm, let me just think of something. Normal distribution. Yeah, so let's say like you just add salt to a dish, and so that is your X, the concentration of salt. And y-axis is taste, whether the taste is good or not. So if your concentration of salt is too less, the taste also will be less. And if you increase the concentration a bit, your taste also will become higher. So up to a certain point of salt concentration, you'll get a nice taste. But if your concentration goes beyond that threshold point, the taste will become bad, right? If there's too much salt, it keeps getting bad. So yeah, that tells something about this distribution. Like as you approach a given mean, your curve is increasing. And after a certain point, your curve will start decreasing. Let's just think of another example as well. Mean, can't say that about. And yeah, let's just think of the classic waiting time for the train. How can I model this? Departure time. Let me think of something. Yeah, I'm just not able to think of some nice
No
explanatory
problem.
example. Yeah, we'll get back to it. Let's see if we can find something while solving problems.
Okay, ma'am. Okay.
Yep. And okay. So we were at this. So this is again like how you can calculate your expectation of X and your variance
Okay. So
of
how
X.
this linear algebra affect?
Yeah, sorry. Okay, yeah. So let's say you have another constant Y. No, let's say Y, like if Y, another random variable is given by A plus B into X. So these are constants. So this Y is derived from your random variable X. So if your another random variable is given by this, your mean, the mean of Y can also be calculated as A plus B into your mean of X. So like the mean of X is your mu, which would be given in your question. So from with the mean of X, you can calculate the mean of Y as well. So we'll look at one example that follows that follows something like this. And from this, your variance of Y can also be calculated as B square into variance of X, which is B square into sigma square. Variance of X is sigma square. So these are just some things that you might need to remember. No, yeah, this and this. And there's one more thing. So let's say X, we know that X is a normal so X is a random variable following a normal distribution with mean mu and variance sigma square. Then you can have a value called Z, which is equal to your random variable X minus your mean divided by standard deviation sigma. So you remember this. So you need to remember this. Z is equal to X minus mu by sigma. So this is called Z transformation. And because your X follows a normal distribution, your Z, Z also will follow a normal distribution. So this is called Z transformation. And it helps in finding the different probability statements about X. So it just makes your calculations easier. So let's see how it makes life easier. And yeah, before that, there are just some more things that you need to know about this curve. So let's say, yeah, this is your normal distribution curve. This is your mean. And we know that this CDF, calculating PDF CDF is it's all about calculating the area between any 2 points in the curve. So this generally it's like either like it's like minus infinity to plus infinity. And it could be like any values here. This is the page number. Yeah. So this is how your curve looks like, your mu. And yeah, this is all your variance. So this is mu minus your standard deviation, mu plus your standard deviation, and so on. So yeah. So if you look at the two ends of a tail, so this is called the tail of your distribution. So if you take this tail and this tail, so let's say alpha minus alpha, sorry, like let's say it's minus A and A. So the area of this region and area of this region will be the same because it's a symmetric curve. And similarly, area of this whole region and area of this whole region will be equal. And area of this region plus area of this region is equal to 1. Your total area, which is your f of x. Phi of x is equal to 1. So then what is the area of this half? So the area of this will be half. Area of this whole region will also be half. So just, yeah, now mathematically to denote it, minus A. This is denoted by alpha. Let me see if I can change colors with my pen. How do I do it? Keep colors. Yeah, anyway. Yeah. So yeah, we have, this is alpha. The area of x is greater than A, right? This is the area beyond A. So x greater than A is equal to alpha. Now let me just make a new slide. What's happening? Let's go back to the curve. Minus A plus A. So this is alpha. If this is alpha, the rest of this region would be 1 minus alpha, right? So your P of x is greater than A is equal to, and also P of x less than minus A. So both of these are equal to alpha. And P of x less than A, which is your blue area, is equal to 1 minus alpha. And if you want to calculate this area, this is also the same as P of x greater than minus A is also equal to 1 minus alpha, because this area is alpha, right? And if you want the rest of this, you just do 1 minus alpha. And yeah, if you have something between, so if you want to calculate something like, let's say you have a, like minus A, minus B, B and A. Let's say you want to calculate the area between this, minus A to B, or just like A to B. So for this, what you need to do, you have to calculate P of x less than A, like you have to calculate the area until this x less than A minus P of x greater than B. Yeah, so if you calculate this, you'll get this value. And one more thing would be between minus A to A. So in this case, you will have 2 alpha minus 1. So how? So P of x less than A is this area. That so P of x less than A will be this whole area, right? So this is 1 minus alpha. And P of x greater than minus A. So this will be again minus, wait, I'm doing something wrong. Yeah, so this is just all of what I discussed right now. A, B, Z, A. All this was discussed. Okay, yeah, we were looking at, let's change the color back to red. So we want the area between this. How do you calculate it? So you have P of like phi of A minus phi of minus A. So this phi of minus A can also be written as phi of, so basically just P of 1 minus P of A, right? So that's what they've done here. So phi of minus A can be written again as, so yeah, to avoid confusion, let's keep it as, so this is alpha minus your P of x greater than minus alpha minus A can also be written as 1 minus P of x less than A. So P of x less than A is alpha. So 1 minus alpha. So that's what they do here. So if you solve this, alpha minus 1 minus into minus plus alpha. So you have 2 alphas is equal to 2 alpha minus 1. So that is what you get here. So if you have two intervals, like something like P of minus 5 to 5, you just have to do 2 alpha minus 1. So this alpha is it's the probability value about A. So let's see all this in the example problems. Slide shows current. So yeah, we saw normal distribution, and because if the distribution is normal distribution for very high number of n, for a very large number of n, like when you have so many random variables, it is easier to calculate a distribution that has a standard normal distribution. So what you do is, if you remember, we saw in last week's lecture, we saw about binomial distribution and Poisson distribution. So these are distributions for discrete random variables. So if you remember, we saw something like, if you want to calculate P of x x less than 6, you need to do a summation of P of 1 plus P of 2 plus P of 3 until P of 6. So this is like a summation. So because we have only 6 values here, you can easily do the summation, right? For your f of x, you can easily do the summation. But what will you do if you have 6,000 random variables? You cannot add 6,000 numbers, right? So in that case, when you have such a high number of random variables, you can approximate your binomial distribution or a Poisson distribution. You can approximate it to the normal distribution. So it's just basically like a transformation. So how you can, so if you remember, your binomial distribution formula was P of X, like X was given by N choose K, P power K into 1 minus P power N minus K. So this was your binomial distribution. So you can approximate that to a normal distribution like this, using this formula. So we just know that Z is equal to X minus mu by standard deviation, right? So we know that in a binomial distribution, your mean of a binomial distribution is NP, and your variance of your binomial distribution is NP into 1 minus P. So you know these. You have to remember these, so you know these, right? So you just apply these values here. So X stays as X. So X is your binomial random variable. Minus mu is NP, you put it here, divided by sigma is your standard deviation. Remember, this is your variance. So square root of your variance is standard deviation. So you just take a square root of NP into 1 minus P. So if you apply this, you'll get a random variable that is approximated to a normal distribution. So this will follow a normal distribution. And your X is will
ऐसे
follow.
क्या बोल रहा था कि संदीप भाई ऐसे ऐसे कर रहे थे? अरे वो ये बोल रहे थे कि मतलब वो मैंने बोला ना, तो वो बोलते कह रहे तभी तो मैं इधर आया हूँ जब तू.
Yeah, sorry about that. I had somebody. Yeah. Yeah, so this is how you approximate a binomial distribution to a normal distribution. And now you'll have the Z value. You can easily calculate your normal distribution for P of Z. So we'll see how we can calculate that. We can use online tools. Well, let me just show it to you now. So there's something like this. So if you have your mean, so for standard normal distribution, your mean will always be 0 and your standard deviation will always be 1. So this is for a standard normal distribution. And let's say X. So X in this case is Z. We calculated Z here, right? Whatever this is, we calculate is Z. Let's say it's just. And if you want P of X less than X, you can get this. So X is 0.5. If you want probability of X less than 0.5, you'll get it. So this is your shade portion. If you want probability of X greater than 0.5, you'll get the value as well for a given mu and sigma. Your mu, so this is for a standard normal distribution following n of 0, 1. So even otherwise, you can directly apply your mean here. Where is the keyboard? So let's say mean 5 and variance of 1. You want X. You want to calculate X less than 10. Sorry, let's have. Your mean is 5. Let's say you want to calculate 7. Yeah, so you want to, so yeah, this is your final probability. Probability of X less than 7 would give you this 0.6. So this is how you can use these tools to solve these. So yeah, coming back to this approximation thing, we have the value of Z. So one more thing that you need to do is instead of X minus NP, you have to add 0.5 to the X. So basically your formula will just become X plus 0.5 minus NP divided by the same thing. Why do you add 0.5? Because binomial distribution is for discrete random variables and normal distribution is for continuous random variables. So this is just something called continuity correction. I'm not sure how you derive at this value, but yeah, you just need to add this 0.5 to your X whenever you apply this formula. So yeah, this approximation is good when when the number of random variables is very high. So basically when your mean is greater than 5 and your variance is greater than 5, this is very useful and it makes calculations easier. So like, yeah, let's just look at an example. The number of bits received in a communication channel. Okay. Assume that the number of bits received in error follows a binomial random variable. And assume that probability is 1 into 10 power minus 5. And your n is 16 into 10 power 6 bits. Then the probability that 150 or fewer, so x is lesser than or equal to 150 errors occur. So you need to calculate x less than or equal to 150. And your upper limit here is 16 million. So yeah, even then it is very hard to do a summation of p of x is equal to 1 plus p of x is equal to 2 until p of x is equal to 150. You can't do a summation for all these. So if you apply a binomial distribution, it will be something like this. Summation of 0 to 150, n choose k into p power, if you substitute the formula, you'll understand. So basically, it's hard to do the summation. So what you can do is you do this approximation. So how do you do the approximation again? X minus n into p. Wait, let's simplify this. Okay, wait. I forgot. P is 1 into 10 power minus 5. P is 1 into 10 power minus 5. N is 16 into 10 power 6, right? Yeah. So you do x plus point. So in this case, we need 150. So x is equal to 150 here. So you just do 150 plus 0.5. So 150 plus 0.5 is 150.5 minus n into p. So 16. So 16 into 10 power 6 into 10 power minus 5 will become 160 divided by, so NP is 160. 160 into 1 minus P. P is 10 power minus 4. So yeah, it's much easier to solve this, right? So you'll get something P of X, you'll get some value. So basically you get P of Z less than equal to minus 0.75. Like if you solve this part, you will get minus 0.75. So now what you do is, you have approximated it to a standard normal distribution. So your mean is 0, variance is, standard deviation is 1. And your Z, your X value here is minus 0.75. Now you just apply it here. 0, 1. No, here is minus 0.5. Yeah, sorry, I'm not able to find minus in my keyboard. Okay, I've written it. So X is 0.75. So you want to calculate it less than. So your probability is 0.22663. See, you get 0.22662. So you saw that how this was very much easier to calculate. Instead of calculating this was easier. So that's when this approximation is useful. And similarly, we saw binomial approximation, and now let's look at Poisson distribution approximation. So we know that Poisson distribution P of X F of X could be given by, what is it? Lambda power K, e power minus lambda divided, e power minus lambda divided by K factorial. So this is your Poisson distribution function. And again, if your K is very large, it's hard to do this. Like K factorial, it's just hard to do it. So you can approximate it using this formula. Z is equal to X minus lambda divided by square root of lambda. Because in a Poisson distribution, your mean and variance both are equal to lambda. So standard deviation is square root of your variance. So you do this. So now this is approximated to a standard normal distribution. So this is again useful if your mean is greater than 5 in a Poisson distribution. So here's an example. The number of radioactive particles passing through a hole follows a Poisson distribution with a mean. Lambda is 1000. We need to calculate probability of X less than or equal to 950. The probability that 950 or fewer particles enter the hole. So in that case, you'll just have, like if you do a Poisson approximation, you'll have to do e power minus lambda into lambda power k, lambda power x. So your x is 0 to 950, right? Divided by x factorial. So you basically need to do a summation from 0 to 950. Again, the summation is difficult. So we do the approximation. What was your approximation? Z minus lambda divided by square root of lambda. So, sorry, Z is equal to x minus lambda. So Z is equal to 950.5 minus 1000 divided by square root of 1000. So if you calculate this, you'll get P of Z less than or equal to minus 1.57. So again, if you go back to your calculator, 0 and 1, and what was it? Minus 1.57. Less than or equal to 950. So your probability is 0.058. See, you got the value. So again, this was much easier than calculating this summation. So this is when this approximation is useful. So now the final, what is the time? Do we have time? Yeah, okay, we have 1 more hour. So yeah, the final one is exponential distribution. It's similar to like geometric distribution that we saw. But yeah, so even here we'll have this term called lambda. You should not get this confused with your Poisson distributions lambda. So in Poisson distribution, lambda was your mean. Your mean is equal to lambda. But here in exponential distribution, your mean is equal to 1 by lambda. It's your inverse of lambda. So this is called rate. So lambda is basically called rate. And 1 by your rate is mean. So yeah, let's look at we are looking at kilograms. We are dealing with kilograms of rice that I buy from a grocery store. So your mean would be kilograms. So what will be the unit of your lambda? The unit of lambda would be kilogram inverse, like per kg. So this is just an inverse relationship between mean and lambda here. Also, your variance is equal to 1 by lambda square for your exponential distribution. And your PDF is lambda e power minus lambda x. Your CDF is 1 minus e power minus lambda x. These are just some things you need to remember. It'll be useful for calculation. And this is how your exponential distribution looks like. It's something like this. It's a curve like this. So you can see for different values of lambda, how the curve is. Okay, suppose the number of kilometers that a car can run before its battery runs out is exponentially distributed with an average value. Your mean actually, so 1 by lambda is equal to 10. If a person desires to take 5,000 kilometers, we want to know the probability that the trip is computed without replacing battery. So you need to calculate probability of x greater than 5. So the trip needs to be completed before 5. And yeah, he replaces the battery after 5,000 kilometers. Why that? Average 10,000, 5,000. So this can also be written as 1 minus f of 5. So f of 5 is e power minus lambda x. We have lambda, here x is 5. Here lambda is 10, we know that. 1 minus e power minus 10 5 are minus 50. So if you solve for this, you'll get the answer. And a similar example, users log into the system, which can be modeled as an exponential process with lambda is equal to 25. So here, the lambda is equal to 25. So your mean is equal to 1 by 25. We don't need this now, but yeah, just saying. So you want to find the probability that there are no logins in an interval of 6 minutes. What? Wait. So this means that there is no login in 6 minutes. But after 6 minutes, there are logins that follow this distribution. So your 6 minutes can also be written as 0.1 hours. So 1 hour is equal to 60 minutes. So 1 minute is equal to 1 by 60 hours. So 6 minutes is equal to 6 by 60. So 1 by 10 is equal to 0.1 hours. So 6 minutes is equal to 0.1 hours. So you need to calculate P of x is greater than 0.1. So if with your exponential distribution, it can be written as e power minus lambda x, your PDF. So you just substitute these values, you'll get the probability. So these are all the questions that were discussed in the lectures by professor. Yeah, we can look at more example problems as well. Yeah, before that, let's have a quick demonstration of how you can model these distributions with R. Yeah, let me just share my screen again. So yeah, if you remember, even in your last week's lecture, we had discrete random variables. The functions were binomial function, Poisson, geometric distribution, and binomial, Bernoulli, and all. Yeah. So yeah, we saw like D binom, P binom, R binom, P Poisson. So even these distributions will follow the similar terms. So D is when you want to calculate the PMF PMF in case of continuous random variables, PDF in case of discrete random variables, and P unif. So we are now looking at uniform distribution. So it's unif. So D unif for PMF, P unif for CDF, Q unif for quantile, R unif for generating random numbers. So similarly for a normal distribution, you'll have D norm, P norm, Q norm, and R norm. And for exponential, you'll similarly have, where is it? We don't have it. We just generate. Yeah, so even for exponential, you'll have dx, px, qx, and rx. So yeah, let's look at the parameters that are used. So let's first look at uniform distribution. If you remember uniform distribution, it's like a line. Yeah, let me just plot this. So this is how you generate the distribution. And if you want to plot it, you need to define your x-axis. So here you have max is equal to 20. Let's just see how the plot looks like till for 30 points. So you define x-axis 1 to 30 and you write this. So you need to specify x, which is a vector indicating the discrete random the values, your random variables. Your minimum is 0 and maximum is 20. So 0 to 20, it follows the distribution 1 by b minus a. And the below 0 and above 20, it follows 0. So that's what this means. If you run this, yeah. Yeah, if you run this, you can see. So 0 to 20, it follows some value. Your probability is 1 by 20, which is 0.05. And above 20, it's 0. So to have a better picture, let's increase the x values. So if you plot, I just extended the x-axis, like I've done -3 to see how the tail looks here, and 25 to see how it looks here. And you can see between 0 to 20, you have the line here, like your probability is 0.05, and otherwise it's 0. So this is a continuous uniform distribution. And similarly, if you want to calculate the CDF, you just want to calculate the area until 5, right? So you define Q is equal to 5, which means you calculate P of X less than equal to 5. So that gives you 0.25. So the area, your PDF for 0 to 5 is 0.25. It gives you the value here. And if you want to calculate P greater than equal to 5, you just need to do 1 minus f of 5. So you need to specify lower tail is equal to false, which is 0.75, like you can see. So 1 minus 0.25 is 0.75. So that's what you get here. And again, quantile is, so what is quantile again? You want to see until which point your PDF, your PMF is 0.6. So yeah, so until 12. So until here, your probability is 0.6. Like your area is 0.6. And if you want to calculate the reverse, like 1 minus this, yeah, you just run a lower tail is equal to false. And now to generate random numbers following a uniform distribution, you just need to specify how many random numbers you need. N is equal to 10. You want 10 random numbers. Again, minimum, maximum has to be 0 to 20. So you can see that you get decimal values. So yeah, a lot of people did not join right at the beginning. So I was saying in the previous class, somebody asked me, when you generate random numbers, do we just get integer values or can we get float as well? So it depends on what distribution you are simulating. So if you're working with a distribution,
Uh,
yeah,
Ma'am, float value, ma'am, the number may be like 8.0,
yes.
8.0 like this. Outcome can be come as 8.0.
Yeah, that is also possible here. So yeah, that's what I'm saying.
But if we look at the other side, that 8.0 come as maybe it's a integer.
You can look at the other values as well. So it,
Ma'am, I just want to ask, it is possible, means every value is come here in
yes, yes.
floating time, but if in some of the some random variable maybe uh, 8.0 like
Yes,
this.
yes, that is possible as well.
But ma'am, it can be count as integer when we get the value of 8.0 like this.
Hmm.
It
Yeah,
can
yes, yes.
it is a integer, no?
Yeah, that is an
So
integer.
huh.
But in general, you need to look at the majority. So majority, you'll get a float. So now basically, but
Okay.
what R gives you is it gives you, so if you're running a uniform, so uniform is for continuous random variables. So continuous random variables could take decimals. So that's why it gives you all decimal numbers. But if you run binomial Poisson geometric distribution, it'll give you only integers because those are for discrete random variables.
Yes, ma'am, I got your point.
That you
But
got.
my question is that in among these float value, one of the value may be like this
Yes, yes, that is possible.
13.0.
That is
Is
possible.
it possible?
Yes, that is possible. Yeah, in that case, like if you're confused, you just look at the other random variables, the random numbers. If everything is an integer, that is a discrete function.
No, ma'am. Means
Yeah, but that is
in
possible.
in
13.0 is possible. Yeah.
multiple choice question we have given like every sample coming out as a float value, but among those one may be written as like 18.0, so it will be count
But yes,
it will not count as
theoretically
a
it's possible.
floating.
Yeah, theoretically it's possible, but
Mm-hmm.
R gives you only such decimals. Like if you run any, like if you run uniform, if you run normal, if you run exponential, it gives you all decimals. But theoretically, it's possible to have an integer data. Like yeah, when you're working and
In our unif,
yeah,
because it's for floating value only.
yes. So that's why R gives you just float.
Okay.
Yeah. Okay, we saw this. And yeah, you also learned that as you increase your number of experiments, your mean and variance of wait. Let's say like we saw that example for this waiting time for the bus, right? Like you wait for 20 minutes until your train arrives. So there we saw that the mean was 10-minute waiting time and your variance was 33.33 minutes. So like when you have random variables, when you do it only for 10, when you just deal with a data set of 10 random variables, you might not get your mean and variance closer to the theoretical values. See, like as you can see here, your mean is 6.9 and your variance is 53. This is very far away from 10 and 33, right? 6 and 10, there's so much difference. 53 and 33 is a huge difference. But when you increase your sample size by 100, you get 10.4. And when you increase it by 1000, you'll get 9.6, which is again closer. Yeah, so when you increase the sample size, your values will approach closer to the theoretical mean and theoretical variance. Like variance for 100, you get 33 exactly. But when you ran with 10, you got just 53. So yeah, this is just something that was discussed in the lectures. And yeah, now we again move on to normal distribution. So
Madam,
D norm,
madam, one request. You continue with the previous year problems, madam.
okay. Is everybody okay with that or like, yeah, I
Because
can skip this part if it's repetitive. I can just carry on with that. Question papers.
Yes,
Yeah,
ma'am.
just let me know if you have any confusion in this code. So this
No,
was
ma'am.
already discussed in Friday's live
Yes,
lecture
yes.
as well. Yeah. Okay. Then I will share the problems from previous year. So how do I share this? Yeah, just give me a minute. So X is a uniformly distributed random variable over the interval 0 to 20. So we need to calculate P of X is between 2 and 7. So this is straightforward. We just saw that example. So, so basically you need to integrate 0 to 20 f of x dx. So 0 to 20, your f of x is 1 by 20. No, sorry. So you need to calculate between 2 and 7. yeah, 2 into 7, 1 by 20 dx. So it's just basically 7 minus 2 divided by 20. 7 minus 2 is 5 by 20 is equal to 1 by 4. So P of this is equal to 1 by 4. And then now we need to calculate x is greater than 6. So this is basically, no, this can also be written as, oh, okay. Greater than 6 is, so 6 to 20. Because your interval is 20 here. 1 by 20 dx. So this will give you 20 minus 6 by 20 is equal to 14 by 20 is equal to 7 by 10. So yeah. So these are the answers to the question. So this was simple. So this question was straightforward. And your second question is also very similar. Same thing. You just need to calculate 1 to 6, 1 by 20 dx. So it's 6 minus 1, 5 by 20. Again 1 by 4. And x is less than 8 is equal to 20 minus 8 by 20. What is 20 minus 8?
Ma'am, 0 to 8.
Or?
Interval 0 to 8. 8 minus 0
Oh,
will
sorry,
come now.
sorry. Yes, sorry. X less than 8, right? Yeah. So it's 0 to 8. So which means 8 minus 0 divided by 20. So 8 by 20. 4, no. 2 4s are 8, 5 4s are 20. So by 5. Yeah. So that's all. That's the answer to this question. And question number 3. Which of the following can be an outcome of the command runif 7, 5 to 10? So basically you should have 7 random numbers within the interval 5 to 10. So this has 1, 2, 3, 4, 5. So not this. So this definitely has more than 7. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. So both of these have 7 numbers. But look at the limits. This has 16. So it does not fall within this interval. So this is not the answer. So this is the answer to the question. So that's how you look at such questions. I think this question was also discussed in Friday's class. But yeah, let me just go through it. So if x is a random variable with mean mu, so and standard deviation is square root of 25 is equal to 5. So phi denotes the distribution function of standard normal variance, and the values of p of x is less than 10. So let's first calculate this, then we'll calculate this. P of x less than 10. So it's basically x minus mu by sigma, right? So 10 minus 5 by sigma is also 5. So 10 minus 5 is 5. 5 by 5 is equal to 1. So P of x less than 10 is equal to P of z minus 1. Because we are calculating the z value here. We are not calculating the probability value. You just remember that. Don't get confused. So when you substitute these values, you're not calculating the probability. You're just calculating what is z. So yeah, z is 1. So it becomes P of z minus 1. So this can be denoted as phi of 1, right? Less than 1. So phi of 1. And P of x greater than minus 5 is equal to P of x minus 5 by 5 greater than. So x is minus 5 by 5 is equal to minus 10 by 5 is equal to minus 2. So this gives us P of Z is greater than or equal to -2. So this is basically, you have -2, you have +2. So Z greater than -2 is this area. So this is also equal to this. This is also equal to P of Z less than, it's sorry, it's equal to P of, no, it is equal to P of Z less than 2. So this can be denoted by phi of 2. So yeah, so this gives you the answer. So P of x less than 10 is phi of 1, and P of x greater than -5 is phi of 2. So this is your answer. Okay, now one more problem. Yeah, similar thing. You need to calculate P of x between x, 15 and 25. So for this, what can you do? You can calculate P of x less than 15. Oh, sorry, P of x less than 25 minus P of x less than 15. So let's transform this to Z values. So you will have, so let's just calculate Z of 15 is equal to 15 minus mu is 5, variance is also 5. I mean, standard deviation is 5. Variance is 25, so standard deviation is 5. So 15 minus 5 is 10 by 5 is equal to 2. So Z of 15, so which means Z, no, wait, I'll get back to that. So let's calculate Z for x is less than 25. So this is 25 minus 5 by 5. 25 minus 5 is 20 by 5 is equal to 4. So from this, what do you get? You get P of Z25 is 4. P of Z less than 4 minus P of Z, Z of 15 is 2. Z less than 2. So now you just, so this is approximated to a standard normal distribution. So now for this, mean is equal to 0, variance is equal to 1, and we have the Z values. So let's calculate for Z less than 4. 0 and 1, your Z is 4. You need to calculate Z less than 4, right? So X less than 4. You need to calculate this. 0.99997. Note it down. Is equal to 0.99. You had 497. Minus. Now you calculate P of Z less than 2. So you get 0.97725. Minus 0.97725. So if you subtract this, what will you get? You should get something like 0.02272. So this is your final answer. So this is your probability between 15 to 25x. This is how you calculate it. So you just need to calculate the Z value first from your X. Then you need to look up these values in your normal distribution table and find the probability. Yeah, was that clear? India. This was the fifth question, sixth question. So the power W dissipated in a resistor is proportional to the square of voltage. So W is equal to CV square. C is some constant. So C is equal to 3. It is given. And V is assumed to have a very good approximation to a normal random variable. So V is actually the random variable that follows the normal distribution, mu comma sigma. So the mu for V is 6 and the standard deviation is 1. But we need to find expectation. We have the mean for V and the standard deviation for V. But now we need to find the mean for W. And we also want to find probability for W greater than equal to, W greater than 120. So let's see how we can do that.
Madam, can you please share that link, madam, that online calculator you are using?
Okay.
Can you please share that link
Let me
in the
just
chat box? In the chat box.
chat box. Yep, I've shared it. So yeah, we need to calculate expectation of W. So expectation of W can be calculated at, so the W is CV square. So we need to calculate expectation of CV square, right? C is a constant, so you bring it out. So you just need to calculate expectation of C into V square. So C stays as such. So C is 3, you keep it. No, let's just keep it as C for now. C.
Calculate expectation of X square from variance formula.
Yeah, exactly. So we had, so E of V square would be variance of V. Variance of V. Variance of V, which is your sigma square. Plus mu of V square. Because, yeah, V square. You just do mu square. So now substituting these values, you'll have 3. So C is equal to 3. 3 into variance of V is 1. Your mu is 6. So since we want V square, 6 square. So you'll have 36 plus 137, 37 into 3, whatever that is. What is 37 into 3? I'm not very fast with this. 37 into 3 would be 111. So your expectation of W would be 111. So yeah, we got the first part. Now we need to calculate this part. So we wanted to calculate P of W greater than 120, right? So now what we have is, so this is actually P of CV square greater than 120. So this is equal to P of V square greater than 120 by 3, because C is equal to 3. What is 120 by 3? 40. And let me write step by step. So this is equal to P of V square greater than 40. So this is actually, from this you'll get P of V greater than square root of 40. Right? What is square root of 40? P of V greater than square root of 40 is something around 6.32455. So square root of 40 is 6.3255. So you need to calculate this. Now let's approximate this to the standard normal distribution. So this gives you X. So X is 6.32455. And your mean for V, your mean of V was 6, if you remember. Mean is 6. Standard deviation is 1. 6 divided by 1. Right? So this gives you P of V greater than, so actually Z, sorry, Z. Z is greater than 6.32 whatever minus 6 gives you 0.32455. So now you have this. So this follows a standard normal distribution 0, 1. So you need to apply this in your calculator. So you need to calculate Z greater than 0.32455. 0.32455. One greater than. So 0.37276. So that is your answer to the question. What was it? I forgot. 0.37276. So this gives you a probability of W greater than 120. Okay. Was that okay? We can move to the next question. Okay. Data indicates that the monthly supply of electricity in a factory. Okay.
Ma'am,
Yes.
what concept we are applying that in the P of we are making some adjustment, no? The X is made it to P. Sorry.
It's not concept. It's just in the question it's given that W is equal to CV square. But we
Okay.
want to know mean for V and standard deviation for V. So from this
Next. I am asking that P of X greater than making that X is to Z, no?
yeah.
Yeah. W is V is make Z. That what concept we apply
That
inside
is
the problem that we are making that.
that is to make it to a standard normal distribution, like 0, 1. So what you can do is you can also do
Adjustment.
yeah, it's just adjustment. So like here in the calculator, we just
One
apply
number greater.
0,
Yeah.
0 and 1. So instead of that, you can just apply whatever you had in the question. You can apply mean is equal to 6, variance of
Okay.
you can
Subtracting same number, multiplying same number, adjustment in
yeah,
the two numbers.
yeah. So here you'll have 6.3, whatever it was. What is it? 6.32455.
Okay.
32455. So you should get the same answer. You still get 3.3727, right? It was the same answer.
Random
0.37.
variable, normal random variable, instead of the standard, if you give normal, you will get the same answer.
Yeah, you'll get the same answer. It's just you have to be careful about these values.
Oh.
Whatever you give here. If you standardize, if you calculate the Z value, mu is always 0. This is always 0 and this is always 1.
For
But
which one?
if
If
you
you use X.
if you calculate Z, if you calculate Z from X, this
Okay.
always becomes 0. Mu is this
Okay.
is
Instead of that, if we calculate by X, we
yeah.
have to keep mu is 0. And
Yeah. Yeah. But otherwise, you can also directly just apply this value and whatever mean was in the question, you can put it in there. Like we saw, you got the same answer there as well.
what is central limit theorem, ma'am? Central limit theorem, the normal variable becomes standard normal sentence infinity. Is it central limit theorem?
Oh, yeah, that's what we just let me. But let's say in this question, we saw your mean was 6. 0, 1, 2, whatever, 2, 6. Your curve was like this. So just for making your calculation simpler, what you're doing is you're shifting this curve, you're shifting your mean to 0. So you're just transforming your all these points so that they shift to 0. How are you transforming this each point? Let's say so you transform this point by so that each point is x here. X minus mu by sigma. So this gives you z, your new curve. So your original curve is around 6. Your new curve z is around 0. So each value of z is x minus mu by sigma if you look at each of these points. It's just you're transforming it for making calculation easier.
Okay. Thank you, ma'am.
Yeah, was this question clear to everybody?
Yes, madam.
Okay. Let us move on to the next. Seventh question. Data indicates that the monthly supply of electricity in a factory is a normal random variable with a mean of 12.08 million watts. Let's just keep it as 12.08 because yeah, everything is million.
Same problem in the assignment, it is coming wrong, ma'am. Sixth problem, similar problem. You apply the same formula, expression of V square, that is W, you want to find. If you apply that, the 360 is coming answer. Options are not available, that expression of W.
Was your value all the same? Let me just quickly check it.
Value C equal to 5.
Oh yeah, so C is equal to 5. Here C was equal to 3. So you
Yeah.
applying the same way, you're not getting the answer.
I mean, yes, the answer is 360. The options are not available here.
You cannot get 360. Your probability always lies within 1, right? Anything
No.
0 to 1 has to be a.
No, ma'am. Expression of W, I am telling.
Oh, okay. Okay, so you get 360, but did you apply the same way? So what was your variance?
The 30, 100. These are the options are in that problem.
Yeah, if it's not in the options, then you just won't be graded for the question. You don't have to worry about that. But yeah, I can confirm and discuss it in the next class, maybe. Like, yeah, if the options are wrong or if there's something else you need to do.
Yeah, same method we applied, but we don't get the correct option. It may be instead of variance, it is given here. Instead of variance, it may be a standard deviation. Suppose if it is a standard deviation,
What was your
is
variance? What was your variance?
36.
So your standard deviation would be 6, right? So did you do that? Or
Yeah.
no, you don't need standard deviation here. Here you directly just apply variance.
Yeah, variance.
Variance
That
is
5
what?
into 36 plus 36, 72. 5 into 72 only coming.
Why are you doing? So is your mean also 6?
Mean also 6. Mean square is 36.
Okay,
Because 5 into is 6.
let me check.
5 into 72, 360.
Yeah, 360. Then yeah, it just must be a mistake with the options.
Okay.
And is the relationship the same? Like W is equal to CV square?
Yes, ma'am. Yes, ma'am.
Okay, then yeah, it just must be a mistake with the options. Yeah, I'll let you know next week.
Okay. Okay. Okay.
But yeah, as
Thank
long as you know to solve it, it's fine. Okay, coming back. Your mean for this question was 12.08. Standard deviation, which is sigma, is equal to 3.1 inches. The probability that the total electricity supply in the next 2 months will exceed 25 million watts. ST is equal to 3.1 million watts. Okay, you need to calculate this. So you have 2 months, next 2 months. So what you need to do is your mean has to be so similar x minus mu by sigma, right? P of x minus mu minus sigma greater than equal to. So what is x here? 25 minus expectation of this. So here what you need to do is, because it's given
12.5.
you have to do 2 into 12.08
Oh,
because it's given electricity supply in the next 2 months. So you just mean is given 12.08 because you're calculating for next 2 months, you have to multiply by 2 divided by your standard deviation is, I think there is a mistake with this. Standard deviation also, I think it's 2 square into 3.1. No, wrong. 2 variance. Oh, wait, let me just. So I think it's 2 square into mm, equation. Where did we see that? No, normal distribution. Where did we see it? Hmm, I just can't find it. Just give me a minute. Yeah, here it is. Yeah. So your variance of y is equal to b square variance of x. Variance of y is equal to b square variance of x. B square 2 months is 4. Variance of x. Let me just calculate this. I did not work it out. 3.1 9.61 into 4.
two into 3.1 only, ma'am.
Sorry.
2 into 3.1.
Yeah, let me just check it. So yeah, you have to do it this way. It's not, oh, 2 into 3.1 also 6.2. Okay, yeah, that was straightforward. Yeah, it's 6.2. So yeah, if you calculate it this way, 2 into 3.1, it's the same thing. Yeah. So solving this, you'll get 6.2. So what will you have now? So this is Z. P of Z greater than 25 minus 12.08 into 2 is 24 point something. It's 24.16. So 25 minus 24.16 is 0.84. 0.84 divided by 6.2. 0.84 divided by 6.2 is P of Z greater than 0.1354. So yeah, now you just have to put this in your table. 24.16. No, did I make a mistake? 25 minus. Okay. Yeah, it's correct. So you just need to apply this. What is it? 0.1354. 0 and 1. 0.1354. What did you want to calculate? X greater than 1, right? So 0.44615 is your answer. So P of X exceeding 25 million watts is 0.44 something. 0.44615. Yep. Yeah. So that's this question. The next one is also a bit similar to this, I guess. Suppose the length of a screw manufactured by a machine normally distributed with mean. What is this?
Ma'am, screen is not visible.
Okay. Did it just happen or? Okay.
Ma'am, now
Last
okay.
problem. Last problem again show it now.
Was it not visible?
Last problem.
Ma'am, visible now.
So where did you lose it? Current. So this was the, I'm sorry, it's a bit lagging. So yeah, this was the previous problem. So because it was given 2 months, you just multiply 2 with your mean and 2 with your standard deviation. And you just do it as usual. You calculate Z and you apply this Z value in your online calculator and you get your probability value. Is it fine? Or? Yeah. I'll just go through. This is also very similar to that, I think. Here mu is equal to 10 centimeters. And your variance is equal to 0.01 centimeter. So variance is sigma square. So your standard deviation is square root of 0.01 is 0.1. And what you must see, calculate probability that X falls between 9.9 and 10.2 centimeters. So basically you need to do, let's first find Z value for 9.9. So Z for 9.9 is equal to 9.9 minus mu is 10 divided by 0.1. So this will give you minus 1. So if you solve this, it will give you minus 1. And Z for 10.2 is equal to 10.2 minus 10 by 0.1 is equal to 0.2 divided by 0.1 is equal to 2. So we have this. So we just need to solve for P of Z less than 2, less than equal to 2 minus, because Z for 10.2 is 2. Upper limit minus lower limit. It's always upper minus lower. So Z less than 2 minus P of Z less than equal to Z for 9.9 is minus 1. Minus 1. So if you just put these value in your table again, you'll get it. 0 and 1 2, you needed less than equal to, right? So 0.97725, 0.97725, and probability of z less than equal to -1. Less than equal to -1 is basically this. Okay, that should be fine. Let's see. -1. Oh. The probability of z less than equal to -0.15866 minus 0.15866. So subtracting these two, you'll get 0.81 something. So this is your final answer for this. So yeah, all these are like very similar patterns. You just need to apply them. Let's just go through this fast because yeah, we're running out. So with R, how will you calculate this? You can calculate this with P norm. Q is equal to 2. No, how do you do this? So yeah, basically for this you need to do like P norm for 2 minus P norm for -1. So P norm Q is equal to 2, comma, mean is equal to 0, comma, SD is equal to, what was your value? 0.1 minus P norm Q is equal to -1. Same, mean is equal to 0, comma, SD is equal to 0.1. So you can do it this way, right? Or you can just directly do P norm 10, Q is equal to 10.2, comma, mean is equal to 10, SD is equal to 0.1. Oh, sorry, here SD is equal to 1. Like for your standard normal distribution, SD is 1. If you want to just directly apply, you do this. SD is equal to 0.1 minus P norm Q is equal to 9.9, comma, same, mean is equal to 10, SD is equal to 0.1. You can do it either way. Either way, you'll get the same answer. It's just showing you different ways of getting. If you use this table also, you'll get the same answer. If you do it with R, like either of these two ways, you'll get the same answer. You can try it out. And then the next question is, which of the following is the correct command in R to compute probability where X is normally distributed? So yeah, we just saw. So we need to do P norm, Q is equal to 25, comma, mean is equal to 5, SD is equal to 4. Variance is equal to 16. So SD is equal to 4. In R, you need to specify SD. So that's what you're doing here. Minus P norm, 15, mean SD. So this is your correct answer. So here, and now we're doing, I think we're doing approximation. No, I don't, let's see. In a radioactive experiment, assume that the number of particles received by target can be, okay. So we're doing approximation here. So we have binomial random variable. Assume that probability of the particle is 0.1. N is equal to 50 bits. So NP is equal to, what is your NP? 5. NP would be 5. So the exact probability that the normal approximation to binomial P of X 2 or less, so X less than equal to 2. You need to calculate this. So we want to calculate a normal approximation. So how do you do it? P of Z less than equal to, how do you do? X plus 0.5 minus NP divided by square root of NP into 1 minus P, right? So we have all these values. We have N, we have a P, we have NP. P of Z less than equal to, we have X. X is 2. 2 plus 0.5 is 2.5 minus NP is 5 divided by square root of 5 into 1 minus 0.1. So if you substitute all these values, you'll get some value. Z is equal to some value. So basically you'll get, so this value will equate to minus 1.18. So if you apply this in the table, you'll get your answer, right? So you can also just do P norm minus 1.18. You'll get the answer. So when you do a standard normal deviation, where your mean is 0, because we have computed Z, right? Standard normal deviation, again, mean is equal to 0, SD is 1. In R, you don't have to specify anything. You can simply just do P norm minus 1.18, you'll get the answer. So yeah, this is just binomial approximation of normal distribution. Normal approximation of binomial distribution. Yeah, we have NP, we just substituted. This is simple, straightforward. Okay, in a large computer network, the logins can be modeled as lambda is equal to 1. What is the probability that there are no logins in the interval exceeding 4 minutes? So you need to calculate probability of x greater than 4. This can also be 1 minus probability of x less than 4. So what is your exponential CDF? So your CDF is like, so CDF for your exponential distribution is 1 minus e power minus lambda, right? So oh, sorry, I think I did a mistake. What is it? Minus lambda x. Yeah. So this is your CDF for exponential. So yeah, we just substituted here. 1 minus e power minus lambda is 1, x is 4. If you substitute this, you'll get 1 minus 1, nothing, 0. And you'll simply have this. Yeah, so basically, wait, let me quickly solve this. One minus exponential of minus 4. So yeah, you get 0.01831. So this is your answer. This is your final answer. The same thing you can also do with R, Px, Q. Q is basically your x value. So Q is equal to 4, comma, your rate is equal to your lambda value. Lambda is equal to 1. And lower tail is false. Why lower tail false? Because we're doing this 1 minus here, right? So you do this. You'll get the same answer. You can try it out. And next question, running, you're already late. Okay. So in a large computer network, user login 4 minutes. The same thing. Find the probability of number of logins per minute between probability 6 and 9. So now what you need to do? The exponential function was 1 minus exponential of 1 minus e power minus lambda x. Lambda is 1, x is 9, and x lower limit is 6. So you need to do 1 minus e power minus 9 minus 1 minus e power minus 6. If you just calculate this, you'll get the answer. Yeah, you can work it out. And yeah. In a large computer network, you have the same thing. So how will you do it with R? Which of the following command in R gives you 8 random variables for this distribution? So you need to generate random variables. So you use Rx, 8 observations. So n is equal to 8. And what is your rate? You have to be careful here. The question, mean is equal to 4. So mean is equal to 1 by lambda. This is equal to 4. 1 by lambda is equal to 4. So your rate means lambda. So you need to find lambda. What is lambda? Lambda is equal to 1 by 4. You just rearrange this. Lambda is equal to 1 by 4. 1 by 4 is 0.25. So your rate should be 0.25. So this is your answer. Number is equal to n is equal to 8, rate is equal to 0.25. Yep, that's all. So these are all the questions discussed in previous year's paper.
Ma'am,
Yep.
syllabus point estimation is there, week 7.
Sorry, I didn't hear you.
Ma'am, point estimation. Hello.
Yeah.
In the syllabus is week 7 portion. Point estimation is there. We have not studied about point estimation here.
You mean point estimation for uniform distribution?
Oh,
Yeah, so that point estimation, I don't know if that's what you're mentioning. So point estimation for a continuous uniform distribution is 0.
point estimation. You're estimating the parameter, no? Parameter, population parameter using sample.
I am not sure. Are you sure
That is
that's
a,
week 7?
yeah, week 7. Shall I share that? It is in the syllabus. Statistical inference and the point estimation is the week 7. But
Madam, there is some lag, madam. There is some lag between the syllabus and what the syllabus has been covered. So that is
Oh,
what sir is asking.
I don't know about
There is
that.
some lag.
That we'll have to
next
ask
week
professor.
coming next week,
Yeah.
next week is there.
Yeah, okay. Maybe it's covered next week. Yeah, it's probably some lag. So yeah, that is up to what professor handles.
Yeah, point. Okay, ma'am. That's
Okay,
okay.
yeah, this was all what I saw from the lectures. This was what
Madam,
was 7.
Madam, one more thing. Like this recorded video will be available at what time, madam?
Tomorrow morning when you wake up, you should find it. It's
Okay.
it's because it's late for me now. It's 12:40 a.m. because
Okay.
I'm not in India. So
Okay.
yeah. So tomorrow
By
when you
10
wake
o'clock.
up by
By
8
10
a.m.
o'clock.
you should find it.
Okay, madam.
Yeah.
Thank you.
In case you don't have the link to the drive, this is for everybody. This is where
Okay.
I'll upload the slides, like whatever we did today, I'll upload it there. And YouTube video should be in my. How do I share the channel? Okay, yeah. This is my YouTube channel. So yeah, the videos, all recordings will be found here. It'll be found in a playlist called NPTEL. Let me check.
Yes, madam.
Yeah, NPTEL Essentials of Data Science 2024. So yeah, everything will be found there. Yeah.
Okay, madam. Tomorrow morning we will get it.
Yeah. By 8 a.m. you should find it.
Okay, madam.
All right. If there's any problem, we could, with your current assignment, we could discuss that next week as well.
Okay, madam. Thank
Yeah.
you.
All right. Thank you.